seats. It sometimes goes Democrat, sometimes goes Republican. So elections tend to be controversial, big, very heavily noticed events there. They use a wide range of technology, all approved by the Ohio Secretary of State. It turns out states have a Secretary of State too. In Ohio, the Secretary of State's job, among other things, is approving the voting technology that's used there. And of course, they buy the same equipment from 3 out of the 4 vendors that every other state is buying from them. So there are only 4 vendors of this stuff, and they're not getting special Ohio voting equipment. They may get the software a little bit customized for them, but basically they're buying the same hardware and largely the same software and firmware as everyone else. So Ohio did an interesting thing last year. Following on the tail of California, which did a comprehensive top-to-bottom review of voting technology that I was involved in, the state of Ohio wanted to do the same thing for their voting technology. And they use, again, 3 of the systems that are 3 of the 4 vendors. California used 3 of the 4 vendors, but not the same 3. So there was not complete overlap. One of the vendor systems, ES&S, had never actually been included in an independent review of the entire system as a whole. So basically, Ohio went to a couple of academic institutions, Penn State and the University of Pennsylvania. I'm at the University of Pennsylvania, and asked us if we'd be willing to do a similar kind of review. So when I got asked to do this, first of all, I mean, an interesting property is when you get phone calls from the Secretary of State, the receptionist tends to deliver that very quickly. I had to explain I wasn't talking about Condoleezza, so it made everyone thought I was much more important than I actually was. But it raised this question of, should we actually be involved in this? Is this a good idea to do? And in particular, the fact that we'd be looking at trade secret code raised some alarm bells. Would this constrain us about what we could say or what we could do in the future? Secondly, would we be able to do a good job? They were asking us to look at an entire system that we had never seen before, that we could never have seen before, hardware, software, firmware, and everything else, in a period of about 2 months. What if we don't find anything? What can you conclude from that? Well, if we find problems, we know there are problems there. But if we don't find problems, it might just be that we were dumb. All right? Maybe we just weren't clever enough. Maybe if we had a little more time, or we're a little bit smarter, there's some looming vulnerability that we didn't find. We would hate to implicitly put our seal of approval on something that, in fact, we're not saying is secure. We're just saying we didn't find any defects. So there's a question of whether or not it's ethical to be involved in a review that's inherently, by its nature, going to be incomplete. Of course, you can't tell that software is free of defects. You can only tell that it has defects that you found. Now, not only can't you tell, it's like the only thing in computer science we can prove is that you can't figure out the answer to this. So this is a really important result that may not be well understood by people reading the outcome of this. So we were a little bit hesitant, and we ultimately decided, we kind of gritted our teeth and said, okay, this may be worth doing anyway. So the first problem that we solved was a very painful contract negotiation in which we had to ensure our independence. So we had to make sure that we would really be able to do an independent review, get access to all of the source code of the system, get access to all of the hardware, have adequate tools for looking at it, conditions that would let us actually do an independent review and not have to take anyone's word for how anything is set up. And most importantly, maintain our editorial control over the output. So one of the things that we were very careful and insistent on was that we wouldn't do it unless we could control the report that we were publishing, that the vendors or political forces wouldn't be able to edit our report before it got published. There would be a published report, it would contain our findings, and no one would be able to censor it after the fact or force us to change any of our findings or anything like that. Now, we did agree that any source code that we were going to use to illustrate things in our report, we would publish in an unpublished annex that would only go to the state. We wouldn't put that in the published report, any actual code snippets from the vendor's secret code, but all of the findings would be in this published report under our control. So that took the first 10 weeks of the project. In the final week, we actually did the work. But we were successful at doing that. So there were 3 academic teams working on this, one at Penn State run by Patrick McDaniel, another at UCSB WebWise Security run by Giovanni Vigna, and then a team at University of Pennsylvania. We divided the systems up by vendor. I was lucky and we got the one that no one had looked at before. So we got to look at the ES&S system that again, nobody had looked at the entire system as a whole before we looked at it. Okay, so why is this hard? Why is it hard to evaluate a voting system? Why do we get 10 weeks to do this? In theory, e-voting is like the simplest problem in the world. You'd imagine that somewhere buried in the voting system, there's a line of code somewhere that says something like, votes candidate equals votes candidate plus 1. Or, if it's in C, votes candidate plus plus. Or, if it's COBOL, add 1 to votes candidate. And, you should be able to do this with grep, right? Look for this line. If it says, plus 2, something's wrong. Or, minus 1, then something's wrong. But if there's that line in there, and it's only in there once, and you can only reach it from one path, then it's a reliable voting system. It's solving this simplest problem in the world. But, in theory, theory and practice are the same. In practice, they're not. So in practice, you've got a lot more than just a voting machine that's doing the tallying of every time you push the button, adding 1 to this counter. You have an election management system, software that defines the ballots, that provisions the voting computers, the DRE machines and the optical scan systems. The firmware running in the hardware that's sent out to the precincts. There's communication. Basically, it may involve SneakerNet, but there's a big communication system for getting the things at the voting locations back to the county headquarters. And maybe it involves modems, or maybe it involves moving memory cards or equipment back and forth. But that system for communicating these results, again, is part of what you have to examine. And then there's this human element. There are procedures that people are following. There are mechanical locks and seals. There are procedures for dealing with the keys, and so on and so on. So, this is actually a pretty complicated system, and the threat model itself is pretty complicated, right? This is not as simple as most other systems, because we have threats that don't exist in anything other than voting. You have the usual things. Can somebody alter data? Can somebody deny service? Can somebody change the official results? Data integrity. But you also have ballot secrecy issues, right? One of the attacks against a voting system is figuring out who someone voted for. A system needs to be secure not just for integrity, but it also has to not have accountability. So somehow you have to have data integrity, but not accountability back to the individual voter, which is not the usual way you do data integrity. So it's a complicated thing. So the system we looked at Penn is the largest